Hey everybody, welcome to today's lecture for analysis of algorithms. Today's lecture is lecture 9 and it's on minimum weighted spanning trees. It's based on section 5.2 in the book, so if you're following along as you should be, you should be able to follow along with section 5.2. Okay, so the minimum weighted spanning tree algorithm is the first one we're going to look at that will consider weighted graphs. Okay, so we've looked at graphs before that have vertices and edges. Okay, and previously we've said that all edges are created equal, but in this circumstance we're saying that actually the edges have some weight attached. So if you look at the example over here, we're saying that we've got a graph that has vertices and edges, but now the edges are annotated with some weight. Okay, now probably the question going through your head right now is, well, what does that weight mean? Well, that actually depends on the problem. So it's possible for this weight to be some concept of a cost. You could say maybe getting from 0 to 1 costs 3. It might, on the other hand, it might be a reward. You might say if I go from 0 to 1, I get a reward of 3. So it's not a fixed definition for what that weight implies, right? Depending on the problem, you could have a different meaning to the weight of a graph, okay? Currently, just think of it as there's some property to an edge which has a value, a numerical value, and that's the weight of the edge. So one quite common problem we want to solve in these weighted graphs is we may want to construct a subgraph that uses less weight. Okay, an example we're going to look at is perhaps a low-cost computer network. So let's say you've got a computer network that looks like this, right? These are your computers and these are your cables between the computers, okay? And these edges represent a cost. So in order to maintain this network connection, it costs us 3, and this one costs 4, and this one costs 2, and this one costs 4. Now, what's interesting about this is, remember, networks allow machines to communicate through other networks. So for instance, if I want to communicate between, say, 4 and 5, I could send a message directly across the line 4, 5, or I could use the line 4, 1, and 1, 5. Okay, so I now have a sort of redundant path. I can either go like this or I can go like this to get from 4 to 5. Okay, but that means I'm incurring a cost which I don't necessarily have to incur. So for instance, over here, I could say, look, I just want to cut out this edge 1, 5. And if I did that, so if I've now got a computer network that looks like this, every machine can still communicate with every other machine, right? Previously, there was the edge 1, 5, so one could talk to 5 directly, but now one has to go through 4 to talk to 5. But that doesn't make a difference, right? It can still communicate, okay? So this network accomplishes the same function as this network, but with less cost. But could it cost even less? Well, yes, right? I mean, that could bring us to the problem of having a minimum weighted graph. So what's the cheapest subgraph of our original graph? Okay, and so if this is our original graph, I mean, this is a subgraph, right? It contains only vertices and edges from this graph. Okay, so this is the cheapest possible subgraph of this graph. Okay, but that's kind of pointless, right? Because I mean, no machine can talk to any other machine if we were using our computer networks example. So this is a pointless subgraph. Yes, it would save us a lot of money to have no network connections, but then we'd have no network connections, right? So what we want is we still want the vertices to be connected, okay? So we redefine the problem. Instead of talking about a minimum weighted graph, we're going to talk about a minimum weighted connected graph. So let's change the problem. Now we say, look, this is our original graph. What's the cheapest connected subgraph of our original graph? Well, now it could just be the vertex 0. This is a subgraph of this. It contains only vertices and edges from the original network. But it's literally one vertex. Is it connected? Well, yes, because 0 can reach itself and there's no other vertices. But, I mean, that's also kind of pointless. Like, yes, we could say it's cheaper to just get rid of all the computers. But, I mean, then we wouldn't have any other computers. So that's kind of pointless. Um, Also, don't you love copy and paste? I got this entire phrase for free. But so what we want to do is we want to make sure we keep all the vertices from the original graph. Okay, and if you remember from your definitions in chapter 3, you did read the definitions in chapter 3, right? Yeah, me neither. The word we're looking for is spanning. Okay, so when we say something is a spanning subgraph, we're saying that it contains all the vertices from the original graph. Okay, so this wouldn't work because this only contains 0. We need a minimum weighted connected spanning graph. This is getting to be quite a long name. Now, if we have a spanning subgraph of the original and we want the cheapest one, now here's the important thing, cheapest. Is it possible that that cheapest one contains cycles? Okay, let's look at an example. Let's say this was our original graph. Okay, if this is the sort of cheapest connected spanning subgraph of our original graph, we can see it contains a cycle 0, 1, 4, right? Then it's always possible to make the graph slightly cheaper by taking out one of the edges from that cycle, right? Because the cycle is like redundant. It's basically saying, like, if you look at 1 and 4, there were 2 ways to get from 1 to 4. I could go this way or I could go this way. And that's why I had a cycle. So I can take out one of those paths and still have a connected graph, right? And taking out an edge will make it cheaper. So that means if I want the cheapest connected spanning subgraph, it's always acyclic. It'll always contain no cycles. So I can sort of take the name minimum weighted connected acyclic spanning graphs. But that's pretty unpleasant to say. And we already know that a connected acyclic graph is a tree. So we can change the name to a minimum weighted spanning tree. Okay. Did that make sense? I know that was a little weird. Well, the point of the minimum weighted spanning tree algorithm is to produce connected subgraphs of our original graph, right? And in particular, to produce the cheapest connected subgraph, spanning subgraph of our original graph, right? And it's easy to see potential uses. Like I say, a very straightforward one could be computer networks, where you say, I want every computer to be able to communicate with every other computer, but I don't want a lot of cost in my cabling, right? So I want to find the cheapest way to connect all of these vertices. And as we go along, we'll see a number of applications, which sometimes I will phrase as TUT questions or possibly even exam questions. But there's always applications to this sort of algorithm. Okay, but so now we've got a definition of the problem. But how do we actually get a minimum weighted spanning tree? So fundamentally what we want to do is we want to say, if we've got this original graph, how do we get this very cheap tree that has all the vertices of this one and is connected? Because if we look at it, I mean, this one here has it's pretty expensive. There's lots of edges to it and they all cost. Whereas this one has a lot less edges. So this one only costs like 14 or something like that, right? Whereas this one's total cost is a lot higher. So the algorithm we're going to use is something called a greedy algorithm. Now, greedy algorithms are the sort of easiest algorithms you get in computer science. What greedy algorithms do is they say, you know what, don't think long term. Just think about right now, right? They kind of go, forget about the long-term consequences and just take the best option right now, which is why we say they're greedy, right? They have no delayed gratification. They're just like, take it now. Okay, so given that we want to construct a minimum weighted spanning tree, what would a greedy algorithm do? Well, given that it wants the best thing right now, it would just always pick the cheapest edge. Okay, so that's the sense in which it is greedy. It doesn't think about long-term consequences of picking the cheapest edge. It'll just pick it. Okay, now let's look at a more formal, but not completely formal. For properly formal, you should look at the book. But for a slightly more formal way of defining the algorithm, let's go forward. So how the algorithm works is we will construct a minimum weighted spanning tree by initially having a tree made up of just one vertex. Okay, so this is our original graph. And what we're going to do is just pick any vertex. It doesn't matter. I picked one, but you could pick 5, 3, 2, 0 to 4. It wouldn't matter, right? So pick any vertex and start off your tree with it. Then repeatedly add the cheapest edge from the original graph that goes from a vertex that's in the tree to another vertex that's not in the tree. Okay? And you just keep doing that, and you stop whenever you have all the vertices from the original tree. So that's why it's straightforward. It says the cheapest edge going from a vertex in the tree, currently the only vertex in the tree is vertex 1, to a vertex not in the tree. So that means it must either be the edge 1, 2, 1, 0, 1, 4, 1, 3, or 1, 5. Okay? Because it goes from something in the tree to something not in the tree. Now, what's the cheapest such edge? This one costs 3, 4, 3, 4, and 2. So it's got to be this one, which costs 2, right? So what we do then is we add that edge to the tree. So our tree now looks like this. We've got the edge 1, 5 in it, which costs 2. And then this thing said repeatedly, so we're just going to do it again. We're going to say add the cheapest edge from the original graph going from a vertex in the tree to a vertex not in the tree. Okay, so now vertex 1 is in the tree and vertex 5 is in the tree. So the cheapest edge going from a vertex in the tree to a vertex not in the tree is perhaps 1, 2 costs 4, 1, 3 costs 3, that one costs 3, that one costs 8, that one costs 4. Okay, so the cheapest is either 1, 0 or 1, 3. Okay, because they both cost 3. Now, this is an important thing to remember. This is probably the most common way people mess up this algorithm is you don't have to continue from where you left off. Right, so we started off with the edge, we start off with the vertex 1, and then we pick the edge 1, 5. We now don't have to carry on from 5, right? That's not part of the algorithm. The algorithm just says add the cheapest edge going from a vertex in the tree to a vertex not in the tree. So it doesn't mean we have to start from 5. We can start from 1 or 5 as we proceed, right? So the cheapest edge is not 5, 4, which costs 8. It's either 1, 0, which costs 3, or 1, 3, which costs 3. And I can pick either one, it doesn't matter. Regardless of which one I pick, I'll end up with a minimum weighted spanning tree, so it doesn't matter. Okay, so I'm going to pick 1, 0, which costs 3. Okay. And then, again, it's said repeatedly, so that means pick the cheapest edge going from a vertex in the tree to a vertex not in the tree, and that's going to be 0, 4, which costs 2. Okay, so I've got the edge 0, 4, which costs 2. Again, pick the cheapest edge going from a vertex in the tree to a vertex not in the tree. Now it's going to be 1, 3, I guess. And so, we keep building this thing up. And again, pick the cheapest edge going from a vertex in the tree to a vertex not in the tree, and I end up with 1, 2 as the cheapest one. And now look, all the vertices from the original graph are in the tree, so we can stop. We're done. And that's our minimum weighted spanning tree. So that's pretty cool. That was quite easy, right? We just continuously just chose the cheapest edge available to us. Okay, so that was pretty cool, but how do we know that it is correct? And by correct, I mean, how do we know that it always results in a minimum weighted spanning tree? It always results in the cheapest possible tree that could have been constructed using with all the vertices from the original graph. Well, happily, there's a proof in the book, so read and understand it. I'll pause while you do. Okay, yeah, I'm just kidding. That proof is unpleasant. I hope you did read it, though. But what I'm going to do is I'm actually going to explain it because I think it's quite a nice proof, actually. Okay, so how do we prove that using this algorithm results in a minimum weighted spanning tree? Okay, so the point is that the algorithm is iterative. As we go through the algorithm, we keep building up a bigger and bigger graph, right? So what we need to prove is that every time we add something, we have a subtree of a minimum weighted spanning tree. Okay? Now, why that would work is because if we always have a subtree of a minimum weighted spanning tree and we make it bigger and bigger and bigger and bigger, eventually we have a minimum weighted spanning tree, right? Because I guess, does it make sense? If we have some like I mean, think of it as any subset. So let's say I said we have some subset of the class in the room. And then I said, continuously, we're just going to add people to the room. Now, if there's always a subset of the class in the room, then as that subset gets bigger and bigger, eventually everyone from the class will be in the room. Okay, so let's see if we can prove this. We're going to use something very similar to induction, but not quite induction. So let's look at how this algorithm will start. When the algorithm starts, the tree is a single vertex. Is this single vertex a subset of the minimum weighted spanning tree, or a subtree of the minimum weighted spanning tree? Well, yes, it is, right? Because this is the minimum weighted spanning tree, and this one is clearly in there. So this is a subtree. Is it a tree? Well, yes, it's connected and acyclic. So that means it's both a subgraph and a tree. So it's a subtree of the minimum weighted spanning tree. Okay, my 3-month-old baby is awake, so I'll be back in a minute. Okay, I'm back, possibly temporarily. So yes, this is a subtree of a minimum weighted spanning tree, right? So we know that at the start we have a subtree of the minimum weighted spanning tree. So the next thing to think about is when we continue, when we add the cheapest edge going from something in the tree to something not in the tree, do we still have a subtree of a minimum weighted spanning tree? Because if we do, then we're good, right? Because we'll just keep doing that and eventually have a minimum weighted spanning tree. So that means what we're trying to prove is that if we start off with a subtree T prime of a minimum weighted spanning tree, which we'll call T, and then we add the cheapest edge going from a vertex in T prime to a vertex not in T prime, then we end up with a new tree, T hash, which is also a subtree of a minimum weighted spanning tree. Okay, so the point is this would be an important result because it's saying that we can start off with a subtree of the minimum weighted spanning tree, and in this case, that subtree is a single vertex, and we can iteratively grow it. We can get bigger and bigger subtrees of the minimum weighted spanning tree until we have a minimum weighted spanning tree. Okay, I'm saying minimum weighted spanning tree a lot. Okay, so if we start with a subtree T prime of a minimum weighted spanning tree, and then we add the cheapest edge xy, which goes from a vertex in T prime to a vertex not in T prime, we end up with a new tree T hash, which is equal to T prime plus xy, which is also a subtree of a minimum weighted spanning tree. Okay, so let's let T be a minimum weighted spanning tree of the graph G, and let T prime be a subtree of that graph. Okay, so we're just writing down the stuff that we already talked about on the top there. Then we say let the cheapest edge in G going from a vertex in T prime to a vertex not in T prime be xy. Okay, so that means xy is the edge we would have chosen if we were running through the algorithm. Okay, so now let's consider this edge xy. This is the edge we're going to add to T prime. Okay, so now there's two possibilities. Either xy is in T, the original minimum weighted spanning tree, or it's not in T. Okay, so let's take the first case. If xy is in T, then T prime plus xy is a subtree of T because, well, T prime was a subtree of T and xy was in T, right? So adding xy to T prime couldn't have made it not a subtree because xy is in T. Okay, so that means T prime plus xy, or T hash, is a subtree of a minimum weighted spanning tree. So we win, right? Everything works out in that case. The other case is that xy is not in T, and that's where things get a little unpleasant. Okay, so if xy is not in T, then T prime plus xy is not a subtree of T, right? Because for it to be a subtree, it has to only have vertices and edges that are in T, and xy is not in T. Okay, so that means that T prime plus xy is not a subtree of our minimum weighted spanning tree. And that's a problem because we said we end up with T hash, which is also a subtree of a minimum weighted spanning tree. But the important thing is we didn't say it had to be a subtree of T. We just said it had to be a subtree of a minimum weighted spanning tree. Okay, so the cool thing is that even though it's not a subtree of T, it could be a subtree of a minimum weighted spanning tree because there could be other minimum weighted spanning trees. Okay, so what we're going to try to show is that T prime plus xy is a subtree of some other minimum weighted spanning tree. Okay, how we're going to do it is Now in T, we said that xy is not an edge, right? But T is a tree, which means there is some path from x to y, right? But it's not the edge xy because xy is not in T. So there's some path that looks something like this: x, v1, v1, v2, v2, v3, all the way up to vny, right? There's some path that goes from x through some vertices to y. There has to be, because T is a tree, so there's a path from every vertex to every other vertex because it's connected. If it wasn't connected, it wouldn't be a tree, and we already said that T is a tree. Okay, now we know that x is in T prime and y is not in T prime, because that's how we chose the edge. Remember, we said xy is the cheapest edge that goes from a vertex in T prime to a vertex not in T prime. So x is in T prime and y is not in T prime. Okay, so that means that on this path between x and y, this one here, there's some point on which we left the tree, right? Because x is in the tree and y is not in the tree. So at some point in this path, we left the tree. Okay, we picked some edge that wasn't in the tree. Okay, that was not in T basically. So not in T prime, sorry. So let's call that edge vi minus 1 vi. Okay, so there's no good reason for that. I could call it anything I wanted. I could call it QR. I just decided to call it vi minus 1 vi. Okay, yeah, I have weird preferences. Okay, so let's construct a new tree T star. And what we're going to do with T star is we're going to say that it's T, the normal minimum weighted spanning tree that we had, but we're going to add in the edge xy. Remember, xy wasn't in T. And we're going to remove the edge vi minus 1 vi. Okay, so this edge that was the first one on the path between x and y that actually left T prime will now be removed, and instead we're going to add xy. Okay, now the point is, when we construct this new tree T star, we know that T prime plus xy is a subtree of T star. How do we know that? Well, T prime was a subtree of T, right? And the only thing that stopped T prime plus xy being a subtree of T is that T didn't have xy, but T star does have xy. Okay, so that means T prime plus xy is a subtree of T star, but we said a subtree of T star, right? Now, so what we're going to do is we're going to show that T star is a minimum weighted spanning tree of G. Because if we can do that, then we're saying that T prime plus xy is a subtree of a minimum weighted spanning tree. In particular, the minimum weighted spanning tree T star. Okay. Well, if we want to prove that T star is a minimum weighted spanning tree, the first thing we have to prove is that it's a tree. So the first question is it connected? Okay, so T was connected, but then we removed vi minus 1 vi. Okay, so it's possible that we remove the only way to get from vi minus 1 to vi. Okay, because we removed that edge. Now, here's the clever thing. We know there was a path that went from x to vi minus 1 and from vi to y. We know that because these vertices were all on the path between x and y, right? There was a path going x, v1, v2, v3, vi minus 1, vi plus 1, all the way up to y, right? There was a path. So that means we could get from x to vi minus 1 and we could get from vi to y. But that's cool because now we've added the edge xy, sort of a short circuit between x and y like this, right? So that means in T star, if we wanted to get from vi minus 1 to vi, we could walk from vi minus 1 to x. We know we can do that because there is a path and it's an undirected graph, right? And then we could walk from x to y because there is the edge xy, we know because we added it. And we could walk from y to vi. So we can go vi minus 1 to x, x to y, and y to vi minus 1, which would be a path from vi minus 1 to vi. Okay, so that means T star is connected because the only thing we removed was this edge vi minus 1 vi, and we can still get from vi minus 1 to vi. So if T was connected, then T star is also connected. Okay, everyone happy with that? So now we know it's connected, but is it a tree? Meaning, is it acyclic? Well, we could try and prove that it has no cycles, but that will be pretty hard. So we're going to take the easy way out. We're going to say, well, we know that T had n-1 edges, right? Because all trees have n-1 edges, okay? So T was connected and had n-1 edges. That's one of the theorems that we talked about last week, and it's at the start of the chapter on trees. It's the start of chapter 5 in your book. Now, we've removed one edge, the edge vi minus 1 vi, and we've added an edge, xy. So if T had n-1 edges, then T star also has n-1 edges. But we already saw that T star was connected. So if T star is connected and has n-1 edges, then it's a tree. Okay, so T star is a tree. So we don't have to bother trying to prove that it's acyclic, because we already have a theorem that says if T star is connected and has n-1 edges, then it's a tree. Okay, so it's a tree, but is it minimum weighted? Well, we know that T was minimum weighted, right? Now T star we defined as being T, and we removed vi minus 1 vi, and we added xy. Now, remember how we chose xy. We said xy was the cheapest edge going from a vertex in T prime to a vertex not in T prime. Okay? But vi minus 1 vi is also a vertex that goes from, it's also an edge that goes from a vertex in T prime to a vertex not in T prime, right? So that means that it's one of the candidates that we rejected when we chose xy, right? We wanted the cheapest one, and we didn't choose vi minus 1 vi, we chose xy. So that means the weight of xy must be less than or equal to the weight of vi minus 1 vi. Okay? Sorry, just to go back a step, remember when we chose vi minus 1 vi, we said it was an edge that goes from a vertex in T prime to a vertex not in T prime. Okay? Just to refresh your memory. And again, we chose xy instead of vi minus 1 vi. And we said we were trying to choose the cheapest one, so xy must be cheaper than vi minus 1 vi, right? But then if we look at this thing, T star is equal to T minus vi minus 1 vi plus xy. And if xy is cheaper than vi minus 1 vi, that means the weight of T star must be less than or equal to the weight of T, because we've removed an edge and then added an edge that's cheaper or the same, right? So T star is cheaper than T, but we said that T was a minimum weighted spanning tree, and it had that word minimum. It was the cheapest possible spanning tree, but the weight of T star is less than or equal to it. So then it must be equal to. It can't be less than, because you can't be less than the minimum, right? But so that means if the weight of T star is the same as the weight of T, then T star must also be a minimum weighted spanning tree of G. Okay? And T prime plus xy is a subtree of T star. We already said that earlier. So that means T prime plus xy is a subtree of a minimum weighted spanning tree. And that's the thing we were trying to prove over here. Right? So now that means if we know that T prime plus xy is a subtree of a minimum weighted spanning tree, that means the algorithm, when it adds edges, always produces a subtree of a minimum weighted spanning tree, which is great, because it means, again, if we have a subtree of a minimum weighted spanning tree that's just increasing in size, eventually it will be the minimum weighted spanning tree. Okay? So what we've shown is that the algorithm produces a minimum weighted spanning tree. Okay, and that's the end of the lecture, which is lucky because baby is awake again. And yeah, I hope that you all enjoyed the lecture. I know the proof was a little unpleasant, but between the lecture and the book, I hope you will understand it. Try not to memorize it so much as understand it. Okay. Often I'll ask proofs that are not quite the proof that is in the book or the lecture, but something slightly different, but that if you understood the proof in the lecture or book, then you are able to come up with the proof you need. Okay, so yeah, what will we do? Yeah, in this week's quiz, you'll get a bunch of questions about minimum weighted spanning trees, and we'll be using the graph marking system this week to test your ability to run through these algorithms. Okay, thank you for listening, everybody.